Okay, so hello everyone. Welcome to the last lecture of this course. Currently, the next Sunday is a holiday, so we have it's a special religious feast dedicated to the destruction of the Second Temple.
Both.
Yes.
They went in the same.
Tzom v'Tammuz.
Yeah.
So thanks to the Assyrian Empire, that will be the last. But I think it's good to stop here because things become more and more complicated. And I think it's quite a right place to stop. Okay, so the last topic of our course will be anomalous Hall effect. And we will be focusing on vial semimetals, mainly in vial semimetals. So anomalous Hall effect is in a vague sense defined as a Hall effect in the absence of applied magnetic field. The definition is really vague because sometimes it also means that Hall effect in the presence of applied magnetic field, but however, the effective magnetic field is much larger, totally different from the magnetic field which is applied. So, but in a vague sense, it's a Hall effect in the magnetic field which is not applied by the experimentalist. However, there is, in some sense, there is a Hall effect, so it means that there is a magnetic field, but this magnetic field is not external, but internal, that comes from whatever origins. And since this definition is very vague, many very different materials fit into these definitions, and many different examples of anomalous Hall effect that I think measure fit into this category. So I'll be focusing on something more specific and more narrow while talking about anomalous Hall effect in vial semimetals. And for me, it would be an example to demonstrate how topological properties of the materials of semimetals come to play and essentially define this effect. So, okay, so I'll start with the favorite Boltzmann equation. As a means to describe a semi-classical transport in this material. However, I claim that the semi-classical equations of motions, as well as collision integral, needs to be modified due to the topological properties of the material. And I'll try to argue explain at least some of the modification. So like I said last time, during our last meeting, the main difference between topological semimetals and ordinary semimetals that before we could think about a problem in terms of a single band. And so electrons were fermions, scalar particles, as opposed to vial or Dirac-like materials, where we have Dirac-like spectrum of more general touching points of two bands of the spectrum, and there we can no longer single out a single band. Rather, we need to talk about some effective spinor that belongs to these two bands, and this will somewhat change the rules of the game. So the first modification is the equation of motion. So when we say r dot, we normally meant velocity, and in our previous consideration, velocity was defined as a derivative of a spectrum with respect to the momentum. So that was our definition of the velocity. And P dot on a semi-classical level was just equal to the force applied to the material, to the electrons in the material, and that was essentially electric field plus plus velocity cross magnetic field divided by C. So this is essentially was the force acting on the electron. Okay, now what and if I want to look at the, say, component I of the momentum, I need to look at the component I of this vector, and this will mean this thing. Okay, now I'm not gonna show it today, but what you can show that the equation for the, so this is essentially Newton's law, yeah? And this is definition of velocity. And the claim is that definition of velocity needs to be modified to account for two additional terms. One of these terms, so let me write R dot component I, so it will be d epsilon of P with respect to I component of the momentum. And now I add two more terms, epsilon I jk, P dot j omega k plus sum over L prime W L L prime times delta R L prime R L component I, where L denotes P and P and Xi, L prime denotes P prime and Xi prime. So here, this guy is essentially, what is it?
Very connection.
Very connection.
No, bare curvature.
But that's my computer. Is it? So it's a curl. So it's a curl of a gauge potential. So is the curl connection or curvature?
Curvature.
Curvature. Okay, then it's bare curvature. So it's the definition of this guy. The definition of this guy is I over 2. This I is the square root of -1, not to be confused with indices. Epsilon I jk. And here will be du over dk j du over dk k minus du over dk k du over dk j. And this is k. So calligraphic k is a momentum, and I, j, k are indices that runs from 0 to 3. So u is a Bloch function, and this object. So let's write me this I is the square root of -1. And this object is very curvature. All right. So apparently, if you look at the equation for the momentum, you see that previously the equation for the momentum has a term with a magnetic field, and equation for the R dot did not have such a term. So the system of equation was very symmetric. Now there is something parallel to the magnetic field on a semi-classical level, and this something is called Berry curvature. So if you take a material with a finite non-trivial Berry connection, you compute its curl, you find that there is a Berry curvature there, and the statement, and I'm not gonna prove it now, that on a semi-classical level, you need to modify equation of motion, and you need to account for this Berry curvature.
What is delta R?
Delta R L prime L, it's the next term, but you also need to add, and this is called accumulation of side jumps. So let me write it here. This is accumulation of the side jumps. And right. So the whole thing here is accumulation of side jumps, and W. So just to finish the definition. So collision integral is just sum over L prime, WL L prime, FL prime minus WL prime L, FL. So W is our familiar scattering probability. Note, there is no Pauli blocking in the collision integral. So that's one of the things that I do not fully understand. Normally, we take a material, we write collision integral with incoming and outgoing terms. There are terms that looks like Pauli blocking, yeah? So WL prime FL 1 minus FL prime minus WL prime L, FL prime 1 minus FL. And then, because this is the flux from one state into another, this is an opposite state, this is the opposite flux, this Pauli blocking, and then we say if WL prime is symmetric, that's conventional logic, then all these things comes down to WL prime FL minus WL prime L FL prime. But that was only if the scattering probability from state L to state L prime was the same as is inverse scattering probability. So that was a textbook logic for many, many years. And then eventually you write a collision integral, which is linear without Pauli blocking, but you explain this thing by just symmetry of the transition amplitude. Now, what's going to happen in the context of anomalous Hall effect? That the scattering amplitude WL prime is not symmetric. I'm going to show you that it's very important for the anomalous Hall effect to have a symmetric WL prime. So essentially, if you have electrons that move in the effective magnetic field, that the probability to scatter from here to there, it's not the same as the probability to scatter from there to here, because there is a preferential direction. So if there is an impurity impeding the motion, then there is a asymmetry. There is a symmetry in the scattering probability, so this event, though it has the same angle of scattering, is less probable than the first event, because there is a magnetic field that kind of turns electron into some preferential direction. So this caricature that I draw here, it's called skew scattering. And skew scattering means that there is a preferential direction of scattering, as opposed which normally happens when there is some effective magnetic field that turns electron into some way. So presence of skew scattering means that WKK prime is not equal to WK prime K. Therefore, according to this naive logic, terms with Pauli blocking should not cancel and be there, according to our logic. However, apparently there is some flaw in our logic, because if you just do microscopic computation, that you can show that these terms with Pauli blocking do not emerge. So this semi-classic picture, which was very plausible and convincing, and appears in our textbook, is somewhat incomplete. And the statement is that you don't need to write Pauli blocking. So the conclusion that we reached with this naive logic was correct. However, this conclusion holds even beyond the situation where scattering amplitudes are symmetric. So apparently that's the right way to define collision integral, even if impurities are non-symmetric. I don't know any semi-classic logic that justifies it, but I know how to justify it with microscopic computations. So that's something where semi-classic logic is not sufficiently developed, at least. Maybe it can be developed, but at least I don't know how to fully explain this in semi-classic logic. Now, okay, so there are two objects that are new here in this equation. One of these objects is pericurvature term in anomalous. So these two terms in the velocity. So this object is essentially velocity. So they're conventional part of the velocity. And there are two additions to this. And the first addition comes from Berry curvature. Another is also associated with Berry curvature, but requires scattering. So the first term exists in the clean material. So if you take semi-metal or any other material as Berry curvature, then there is this addition to the velocity term coming solely from Berry curvature. And to have this term, you don't need to have any disorder whatsoever. So this term is just there, and it was missed in solid state physics for, I don't know how, 100 years. So it's just there, and it should have been there from very beginning, but people just did not realize that this term exists. And the first one who noticed the existence of this term was Latinger. And he essentially wrote it in somewhere in the 60s. And people did not believe him at the time because, well, nobody knew about Berry curvature back then, and he was not sufficiently, his definition was not sufficiently geometric, so he essentially wrote the right object, but without calling Berry curvature. And since people never heard of it, they say that he's wrong, but he wasn't. Okay, so this is the first thing. And there is one more term which is called a side jump or accumulated side jump. And it requires two things. It requires Berry curvature and also impurity. And what this thing roughly does is that if you have many impurities and you scatter of these impurities preferentially, then roughly speaking, what your electron does, it moves slightly to the left each time it scatters. I'm drawing a very primitive caricature. So it means that there is an overall kind of a drift in certain direction, which is proportional to the rate of scattering, and there's some drift velocity. Very hand-wavingly, I'm gonna compute this drift velocity. So, and this is the accumulated side jump, and you need to add this term to the Boltzmann equation. Now, we did some microscopic computation, very rigorous microscopic calculation using diagrams with my student Yoni, and we can show that all this is correct. However, the physical interpretation is somewhat hand-waving. That's the best that I know by now, and that's the best which is in the literature. So let me present you some vague semi-classical picture. It's incomplete in my mind, but that's the best we know by now, and it's correct. We can prove it using diagrams. So how we show this thing? So first of all, let's start with the clean Hamiltonian, and we have wave functions of this Hamiltonian. So these are exact states of a Hamiltonian. So if you apply Hamiltonian on these objects, you get they satisfy well, sorry, I probably should have written it like this. And the time evolution of this guy is something like that. So now let us think about this problem semi-classically, what it means semi-classically. Let's try to construct a wave packet of these states. So we will think about electrons that are peaked at some momentum, characteristic momentum K, 0 as a function of R and T, which will be a superposition of the exact states of Hamiltonian. So these are exact states, and this is the linear superposition. So there is this function of K minus K0. So somewhere there is a typical momentum K0, and it means that all these things are centered somewhat around this typical momentum. I'm constructing a wave packet which is localized both in K and R, and I can think about this wave packet as a classical particle. This is always very dangerous and always on the board of the validity of any reasonable argument, but that's the semi-classical way of thinking. Let's try to do it, and hopefully we'll get away with it. Okay, so then it means that the electron has a coordinate. So what is the coordinate? Coordinate of the electron with the momentum K0 at time t would be just an integral dr of this wave packet at with the operator R. So this is the coordinate of electron with momentum K0. So my electron has a momentum K0 and coordinate R. I'm trying to play both, use quantum mechanics and violate it at the same time. Okay, so let us now plug this definition into this equation, right? So this guy enters into here and into there. So what do I get? I get an integral with respect to R, integral over K1 and K2, W bar K1 minus K0, psi star K1 R and T, R, W K2 minus K0, psi K2 R and T. Okay, now I say, okay, so these guys are wave functions of a Hamiltonian. So I know that they are actually E minus I K T plus I K R times U K of R. This is my Bloch part of the wave function. This is the oscillating exponent. So let me plug this in. So now I'm getting something very long. dr integral dk1 dk2, w star k1 minus k0, w k2 minus k0. And then I'm getting exponent of I epsilon k2 minus epsilon k1 times t. And here instead of r, let me write it as minus I times d over dk1 of acting on E I k1 minus k2 times r. So this is the complicated way to write r times exponent. And then I multiplied by u of uk1 star r uk2 of r. Okay, then with this thing, I now can move the derivative. I can take this derivative with respect to k1 and shift it from this object. Oh, probably let me first of all shift the exponent. So let me take this exponent and move it there. So I'm just writing this exponent there, ei epsilon k2 minus epsilon k1 times t. And then I erase this exponent. And then I take this d over dk1 and move it there. So it means that I'm writing here d over dk1, and now it acts on entire things here, and I remove it from there. Okay, so what did I gain? I gained that the whole thing now can be written as I integral over dr, integral dk1, dk2, w star k1 minus k0, wk2 minus k0, ei k1 minus k2 times r. And here, minus it d epsilon k1 over dk1, u star k1 of r, u k2 of r, plus du star k1 of r, dk1, u k2 of r. All these times ei epsilon k1 minus epsilon k2 times t. Okay, so what do I do next? I now can integrate with respect to delta r, with respect to r, which transforms this object into a delta function. And therefore, there is this integral produces delta function of r1 minus r2 of k1 minus k2, k1 minus k2. And therefore, I now can get rid of one of these integrals, say of k2, and replace the second component with the first. And then this exponent is gone. And what it means that I'm getting that the whole thing will be equal to the integral over dk1, w star k1 minus k0, wk1 minus k0 times minus I c v of k1 plus I du star over dk times u of k, say k1. And then if this thing is sufficiently narrow and sufficiently well normalized, it peaked at k0. So I'm getting something which is minus it v of k0 plus I du star over dk at k0 U of K0. Or if you want U over dk, U over dk at K equal to K0. Sorry, and I was not careful with I is not here. Okay, so what we showed that there is what we computed the coordinate of electron at the momentum K0 at time t, and we found that it's equal to T times VK0 plus I du star over dk uk at K equal to K0. So this is not very surprising. It means that the electron at the momentum K0 goes with velocity, some constant velocity. So this is coordinate, this is time. This is the constant velocity. However, there is a shift, so to say, of coordinate, something that defines this thing at, say, at time 0. This is or time minus infinity. And this is this delta R at minus infinity. Now it's more like 0 in my set of definition, but in the literature, they define that they are at minus infinity. So there is an offset of the coordinate. There is an offset of the coordinate that comes from this very curvature-like term. So that was a propagation of a wave packet, just free propagation, and we just got some a position shift in this propagation. Now what we'll analyze next, we're gonna apply the same logic and now imagine that we have this wave packet coming and there's some impurity on our wave. So this electron comes and scatters of this impurity. So we will now solve the scattering problem. But instead of solving this scattering problem just for electrons, we'll solve this problem for this superposition of states. Okay, so there is an incoming, so it means there is an incoming state and there is an outgoing state connected via scattering matrix. And we will represent the outgoing state of at the energy K, at the momentum K, R and T as some superposition of K prime, CK prime T, psi K prime R and T. These guys are eigenstates of the Hamiltonian. And let's do this thing in the lowest Born approximation. Let's assume that this impurity is weak and we are doing lowest order Born approximation. Then, so in the lowest Born approximation, we can show that this thing will be just minus matrix element of this impurity, K prime, and an integral from minus infinity till T, exponent I epsilon K prime minus epsilon K times T prime dt prime plus delta function of K prime minus K. So it means that C of K prime and T will be minus 2 pi I matrix element K V K prime delta function epsilon K minus epsilon K prime plus delta function of K minus K prime. So it's incoming wave plus a scattered wave. Now let us compute classical coordinate of an electron after scattering. So coordinate after scattering, R of T, will be now equal to the integral over dr, psi out as a function of R and T, R psi out as a function of R and T. This is the classical version of position of particle. And now we plug in our result for the outgoing scattering state. So it will be dk prime, ck prime, ck prime absolute value square vk prime t plus, okay, here I'm jumping, so you need to play a little bit with this expression, but this is what you eventually show u of k prime minus d over dk plus d over dk prime argument of matrix element, close the brackets. And you can identify this and can say this is essentially integral over dk prime, matrix element from the state k0 to state k prime, vk prime t plus uk prime I d over dk prime uk prime minus d over dk plus d over dk prime argument of this k vk prime. Okay, then we can compare their position. So there is a, as you see, there is a just a second. There is a position of the particle as it propagates this time after the scattering, and therefore we can say that this position as a function of time is essentially integral over dk prime w k0 k prime times something that we can symbolically denote drk and k prime. And by looking at this expression above, drk and k prime will be equal to uk prime id over dk uk minus uk I du k minus d over dk plus d over dk prime argument of k vk prime. And this guy is called accumulated side jump. I repeated this logic, so this is the best that the brightest minds came up with. It's relatively recent. I can testify that this result is actually correct in the lowest Born approximation if you perform computation diagrammatically exactly and just look at what happens in the limit of Born approximation. So this result is essentially correct. For me, the logic is a bit vague and semi-classical derivations are a bit mysterious, but that's the best which is known so far. I know that these results are correct. Whether you can come up with a better interpretation, it's a good question. So anyway, so I wanted to say there are two messages right now. There's message number one, you modify the velocity. There are two terms. One is Berry curvature, and this one you can actually show very rigorously. And another one is accumulated side jump. So now if we believe into this thing, let us now focus on Weil semi-metal. Semi-metal. Let me give you a Hamiltonian of my favorite Weil semi-metal. Sigma y plus pz square over 2m minus lambda times sigma z plus this order. So the first line is a bare part of the Hamiltonian. So what this thing describes, it describes two Weil nodes that are separated by delta k, distance delta k being something proportional to the square root of 2m lambda. So this parameter lambda essentially defines the degree of separation of Weil nodes. And in other words, it defines the violation of time reversal symmetry in the problem. So when we have this finite lambda, it means that the time reversal symmetry is broken. As we know, we need to break either time reversal or inversion. So here in this case, we break time reversal. We only have two Weil nodes, which is the minimal number of Weil nodes we allow to have in the problem. So now let us see what does it mean for the anomalous hole. And the first situation, and this is the simplest situation, happens when the chemical potential is tuned just at the Weil node. So we are precisely at the neutrality point, all these states below are filled and all states above empty. Okay, then we just use this approach and say the following. So there is a current, and we know that current is a sum over L. Let's call that, remind you, L was defined as U alpha and K. So essentially we're summing over bands and momentum. FL, and here will be gradient of epsilon L plus electric field times this Berry connection plus side jump accumulation term. So this will be a current in the presence of all these things. Now, since we are at the neutrality point, we can show that this term and that term do not contribute at all. Therefore, the whole thing is equal to the sum over L distribution function times electric field cross Berry curvature. So it means that sigma xy, and it's called intrinsic because impurities do not enter into this object, is just sum over all occupied states, Berry curvature Z component.
So sorry, I think there is a mistake. So you plug in R dot R, right?
Right.
Mm-hmm. So the second term there will be not E, but P.
But P, no, it will be P dot.
P dot, yes.
But P dot is electric field. Okay.
Oh, okay, you don't. Okay,
so
you
this
don't
is P dot. No, I don't have magnetic field. And P dot is in the linear response E. And therefore I plug there E. And then within linear response, I'm getting this thing. and now and end up with something which is just summation of all occupied states of the Berry curvature. And people love this because this is purely topological or purely geometrical, depending on what you like more, because it just sums the total curvature of the occupied states, and you can compute it and show that this thing is equal to E square over 2H times delta K, where delta K is the distance in the K space between Weyl nodes. So if you know the spectrum of your material, then precisely at the neutrality point, the whole conductivity is quantized. So it's precisely equal to E square over 2H times the distance between Weyl nodes. Now, since delta K is material specific, it's not real quantization, but since it's a beautiful formula, this quantization ended up enormously cited paper, like thousands of citations. Now, and this is indeed very, very nice effect that shows that intrinsic conductivity is quantized. So what I mean intrinsic, it means that impurities, disorder plays no role whatsoever. So if you have a Weyl semimetal and you manage to control its filling and put your chemical potential precisely at the Weyl node, you will have a whole conductivity that is completely disorder independent and purely determined by its spectrum. Okay, this is very nice, of course. And the last point that I want to discuss is what happens when you move the chemical potential away from the Weyl node. Now, this is quite interesting because essentially we know that there are many materials like gold, for example, that have Weyl nodes somewhere deeply in the spectrum, but the problem is that normally the value of chemical potential is very far from the Weyl nodes. So of course you can refer to these crossing points as Weyl nodes, and you can still think about gold as a Weyl semimetal, but of course it's jumping very far from the reality because it's more like a normal metal. So what happens here is that as you start to fill the state, so you start to create a small pocket like Fermi surfaces. So when you deviate from the neutrality point even further, these Fermi surfaces become bigger, and at some point, what happens is what is called Lifshitz transition. So these Fermi surfaces merge into a single Fermi surface. And as you go even further, it becomes a Fermi surface, a single Fermi surface, which is indistinguishable from any other metal. But it's true that deeply in the conduction band, there is some special points of touching, which normally play no role. However, it makes sense to think and explore what happens to the Weyl semimetal if we deviate from this filling and move from this special filling toward generic filling. And this essentially tells us that anomalous hole in Weyl semimetal is not conceptually very much different from anomalous hole in any other metals. So it means that there is indeed a very special channel which survives precisely at the neutrality point. But as you deviate, in addition to this contribution, in addition to this purely geometric contribution, you will have a finite contribution coming from the Fermi surface. And people would call this contribution, typically they would refer to it as extrinsic contribution. So this contribution will depend on the degree of disorder in this material. Okay, and so now, so we will essentially have two channels of Hall effect. One is called extrinsic, one is called intrinsic. And I'm claiming that essentially we can compute the extrinsic contribution of conductivity. And my statement is that in a sufficiently large space of parameters, it will be determined by skew scattering. So precisely this mechanism where leptons prefer to scatter of impurity in one direction rather than into another. So there will be a preferential direction of scattering, and this will account for the majority, vast amount of data in this thing. So how do we compute? I'll just outline the main idea of computing the skew conductivity. So the problem is enormously complicated. However, you can realize that there is one limit, and this is the limit which is analogous of S-wave approximation, S-wave scattering. So normally we know that if impurities are much smaller than the wavelength of the electron, we can apply S-wave scattering and say electrons scatter uniformly of this impurity. So outgoing wave is just completely isotropic. This happens when electrons are just scalar and not spinors. So as it turns out, there is a counterpart, there is an analog of S-wave scattering for Weil semimetal. And the difference is that as opposed to scalar case, now we will have two scattering phases for spinor state, spinors with total angular momentum plus minus 1/2. So there is no single scattering phase, but there are two scattering phases for spinor electrons in Weil semimetal if there is a small size impurity. And one can write a whole resistivity in terms of these scattering phases. I'm writing to the final formula. This is based on our own unpublished results that we will gonna publish soon. But it turns out that you can just compute the entire extrinsic contribution and express it in terms of scattering phases. Plus minus rho xx square sigma xy intrinsic. So here rho is a scattering, is a resistance matrix. Sigma is rho minus 1. This intrinsic contribution is something that I showed you a minute ago. It's equal to E square over H times delta K. And the dominant part of extrinsic contribution, something that knows about impurity concentration, can be expressed in terms of scattering phases. So what it means that if you have a Weil semimetal and sufficiently small impurities, you can characterize these impurities by two scattering phases. Now, if these two scattering phases are the same, this term is gone because it's proportional to the difference between scattering phases. However, if these scattering phases are different, it means that there is a preferential direction of scattering, and this what gives rise to the anomalous Hall effect. So for any experimentalist, if you have a Weil semimetal, there are two essential contributions. One is purely geometric that survives even at the neutrality point, and another is extrinsic. And you can characterize the extrinsic contribution of by two scattering phases in the problem. So you either computed or fitted to the experiment, but this is the minimal number of parameters that you need to explain anomalous hole in the minimal model with only 2 while nodes and only 1 type of impurity. Of course, you can make the problem enormously complicated. You can have 40 while nodes and so on, and have very complicated impurities, but apparently it's enough to have a finite but not zero size impurity. It gives rise to 2 scattering phases, which are in general are different. We were able to compute these phases analytically. So we have expression for the scattering phases in terms of impurity size and the potential. You plug it into this formula, and this explains anomalous hole in the Weil semi-metal. So I think this is pushing the semi-classical description to a very non-trivial materials, and I think that it still enables to understand the properties of this material. So I think it's not. It's rather nice that you can use this description and explain anomalous hole. So I guess that's all what I had to say. It's sufficiently, I think it's sufficiently complicated technically by now. Last part is not fully understood in terms of semi-classics. We see that some building blocks can be very transparent, as a building block opaque. So we can justify it diagrammatically, but it will be nice to have a better physical understanding of all these results. Okay, people, don't forget there were 3 home assignments that we need to submit for those who are submitting them. And I guess that's everything.
What's the deadline to submit all the homework?
Just before the next semester starts.
So like this, the contribution, extrinsic contribution comes from the side jump.
No, it comes entirely from skew scattering. So I talk a lot about side jumps and all this to say that I'm sorry, it's totally disorganized. So there are 3 anomalous things. One is simplest to understand, and I didn't explain it at all. And that's something which you can put on really rigorous basis. And this is Berry curvature contribution. You just compute Berry curvature, and you can show very straightforwardly that this term needs to be added to Boltzmann equation, and this is something that leads to E square over H times delta K. This is this term, something which is important to intrinsic scattering. Doesn't know about impurity whatsoever. Then there are things that know about impurity scattering, and they are roughly divided into following. There is a skew scattering, something that tells that this way of scattering is better than that way of scattering. This is good, this is bad. Because there is effective magnetic field. This is skew scattering. This is the most dominant for anomalous hole in the big part of the parameter space. In addition to it, there are 2 more effects. One more effect called accumulated side jump. It's something that I talk for a very long time at the beginning because it's something which is the most mysterious for me to understand. Luckily, this effect is less relevant of all, and you just can safely ignore it except for some very special points in the phase space. So if the impurity happens to be, okay, there are some special cases where side jumps play a role, but you need really to fine tune the strength of the impurities to have for them to play a role. If impurity concentration is sufficiently low, you can disregard these side jumps altogether. I have no intuition why side jumps are not really important as opposed to skew scattering, but that's the result of computation. So skew scattering is easy to understand. This thing is better than that thing. Side jumps are mysterious, only emerge in the context of anomalous Hall effect and have very vague interpretation. That's why I decided to do my best and reinterpret them. So it essentially tells you that each time electron scatters, it drifts into a preferential direction. So there's a preferential direction of a drift that associated with the scattering. So it's not that there's one effect that electron scatters to the right with a high probability to the left. There's also another, this is called skew scattering. There's another effect that when each time it scatters, its center of position shifts. So it goes more or less with the same velocity, but there's a shift of the position, and therefore this works as if there is an additional contribution to the velocity. This is called side jump accumulation. How come that people never thought about this before? I don't really know. But in principle, there are regimes where these accumulated side jumps play a role. Now, if it happens that it plays no role, and this is what happens in the majority of the phase space, then there are two origins of anomalous Hall. One is purely geometrical, E square of h times the distance between while nodes, and another one is coming from skew scattering. Now, skew scattering is something that has to do with the asymmetry of scattering, and that's why it's proportional to the difference between scattering phases. So if you would look in the lowest Born approximation, this effect will vanish. Because in the lowest Born approximation, the scattering phase delta plus and the scattering phase delta minus are the same.
This effect should exist in just in
Exactly, that was my point. And I tried to articulate.
Is it the same formula?
Exactly, yes. Sorry, thanks for pointing it. That's why I was talking about gold. Now, if you take Weil semi-metal and start deviating from Weil node and go very, very far, even passing the Lifshitz transition, then you will have just an ordinary metal. And you will have the metal, and you will have some complicated Fermi surface, and you will have this Fermi surface in any generic metal, gold or any other material. And in this case, the equation, the result for skew scattering will be absolutely the same. So regardless of the material, we start thinking about this problem in the context of Weil semi-metal, but now we realize that regardless of the material, you take any material whatsoever, you take an impurity which has a smaller size than electron wavelengths, so you can think of them as scatters. And then if you want to explain the extrinsic mechanism of anomalous Hall, all what you need to do is to compute the scattering phases for spinors. And it turns out that there are two leading channels of scattering. One for the spinors with the total angular momentum plus half, and another for the angular momentum minus half. So this is an extension of S-wave scattering for spinors, for materials with asymmetric spectrum. And then in terms of these two scattering phases, you can write absolutely generic formula for any spectrum, for any material, saying that the extrinsic Hall conductivity can be expressed in terms of two scattering phases like this, and this is absolutely generic for any material. And this formula should be in the textbook for a very long time. But we couldn't find it in the textbook. So we are writing a paper about it.
So the first term doesn't exist at neutrality point because probably because your Fermi surface is just a point.
Yes,
and you cannot scatter within a point, something
exactly
like that.
Exactly. So you cannot talk about it because essentially there are density of states vanishes And now, since density of state vanishes, all the scattering phases, they know about the density of state, they know about energy. So when density of state vanishes, these scattering phases will be zero. But as you said in words, there are no electrons there because there's no density of state zero, therefore there will be no electrons, and formally this scattering phase will vanish fast enough, such that this part of contribution will be zero. And therefore, close to the neutrality point, people who discuss this intrinsic channel are absolutely right. There will be a quantization, quantization of anomalous Hall conductance. But then as you deviate from there, there'll be another contribution coming from skew scattering. And at a certain point, this contribution will dominate, because essentially you're moving from this very special point to a generic metal with a time reversal symmetry broken. And that's what I'm saying. In that case, everything will be determined by extrinsic contribution, something that knows about impurities. But nevertheless, there is a general formula that you can describe this intrinsic contribution just in terms of scattering phases. And then if you're able to control the filling factor, for example, by changing chemistry, and this is what people do, one of the real experiments that I've seen, then you should see a crossover from one regime into another. That's what I wanted to say. Okay, I guess we can stop this meeting.